Today we're going to focus on a review of, first of all, circles, and then we're going to review function notation and the basics of working with functions. So in algebra, we learned a formula for the distance between 2 points, one of which was called x1 and y1, another which was called x2 and y2. If you wanted to find the distance between these 2 points, then you could take the square root of the following quantity. You could take x2, the final x, minus the initial x, and square that difference. And then you could take the difference between the y's and square that result. Then add those two numbers together and take the square root of whatever you get after you do that sum. For an example, someone asks me for the distance between -1, 2 and 3, 0. So I would say, okay, I'll take my final x, which is 3, and subtract my initial x, which is -1, and then I'll square the result. I'll take my final y, which is 0, and subtract my initial y, which is 2, and then square the result. So 3 take away -1 is equal to +4. 0 take away -2 is equal to -2. Now 4 squared is equal to 16. And -2 multiplied by itself is equal to +4. So the distance between these 2 points would be equal to the square root of 20, which is approximately 4.5 units. Now let's use that distance formula to write down a mathematical statement, a mathematical equation, which is equivalent to the following statement in English. They say, the statement I want you to translate into Mathish is this: the distance between AB and XY is R. Now the word is gets my attention immediately, because the translation of the English word is into mathematics is that is equivalent to equal sign. So is R, I will turn into equals R. How will I translate the distance between AB and XY? I have a formula to translate that distance into Mathish. The square root of the final x minus the initial x, x minus a, quantity squared, plus the second y minus the first y, y minus b, quantity squared. So this would be the translation of the given English statement into mathematics. Now suppose that I wanted to take the same statement and represent it using a picture. Then I would locate my point AB, and I would think about AB as being the location of maybe a post in the ground, a post to which a rope of length R is attached. If a little dog attached to that rope of length R was allowed to roam around the post, the points that it would trace out would form a circle if it could go R units in any direction. So this would be the pictorial example of the set of all points xy whose distance from AB was equal to R units. These points would form a circle of radius R around the center. So what we have obtained in this exercise is a formula that can be used to express the equation of a given circle. A circle is a set of points which are located a fixed distance from a given central location. And the equation of a circle with radius R and center AB is given by the square root of the x minus the a plus the y minus the b, both squared, has to be equal to the radius. Now there is another expression of this same equation which is slightly more common. If you square both sides, then the r on the right will become squared, and the square and the square root will cancel on the left, giving you x minus a quantity squared plus y minus b quantity squared equals r squared. This is the equation of a circle with a radius of r and a center at the point a, comma b. For example, someone says, what is the center and the radius of the circle given below? X minus 3 squared plus y plus 1 squared equals 16. To see the true values of a and b and r, I'm going to start by rewriting this equation in a format that's more similar to what I have above. Now I already have x minus number squared, but I don't have y minus number presently. I have y plus 1. So instead, I'm going to take that plus and rewrite it as minus negative 1. I have a 16 on the far right. In the equation that I was given, I have an r squared on the far right. So I'm going to write that 16 down as something squared. 16 is equal to 4 squared. So now I can identify on sight the values of a and b and r. The center is located at the point AB, which in this case is 3, comma, minus 1. And the radius, usually denoted by r, in this case would be 4. 4 units, the square root of 16. Now, what about the equation below? X squared plus y squared equals 5. Once again, if I want to be able to see the center and see the radius, one way to accomplish this is to rewrite this equation into a more standardized format. X minus something squared plus y minus something squared is equal to something squared. But in my given equation, nothing has been added to or subtracted from x. So it's x minus nothing squared. Nothing has been added to or subtracted from y. So I have y minus nothing squared. Now what about 5? 5 is equal to what quantity squared? If I put the square root of 5 here, then the square root and the square would cancel each other out, and this expression on the right would be equivalent to 5. So from this, I can now read off the values of the center. A, B are both equal to 0, and the radius is equal to the square root of the 5 that was on the far right side. The radius was the square root of 5. So this is how we can determine the center and the radius of a circle given its equation. Compare what you are given to the generic formula for the equation of a circle with a radius of r and a center of AB. The a and the b are the numbers that are being subtracted from x and y inside the parenthesis. And r is the square root of whatever number appears on the right side of your equation. Here our number was 16, so the r was equal to 4. Here our number was 5, so the radius was the square root of 5. In part 2 of this video, let us do a review of functions. A function, fundamentally, was a technique or a procedure. It told you how to take a inputted number and transform it into another number, which was called the output. Now, functions, since they are just procedures, could theoretically be described just in words. For example, someone could say, here's your function, here's your procedure. Take your inputted number, square that number, and then add 1. So based on that procedure, let's determine the output of this function if our input number was -2. So following the procedure, I would say, okay, first they want me to take the input of -2, then they want me to square it. So -2 multiplied by itself is +4. Then they want me to add 1. So if I add 1 to 4, now I have 5. And so this number, based on the given procedure, would be the function's output if the input is -2. But writing down functions in words like this is a huge pain. So for shorthand, we've introduced something that's called function notation. Function notation is a shorthand used to symbolically express questions like the one above. If I were to rewrite this example using function notation, it would look something like this. The procedure is, take your input, square it, and then add 1 to the result. Determine the output if the input is -2. What they want me to do is to square the input. By giving me the number 2 inside the parenthesis, they've specified that the input number is -2. So let's find the corresponding output number. What happens to -2 after you run it through the function which is called f? So I will square the number -2, the quantity in parenthesis -2 squared, plus 1, result 5. The input is whatever appears between the parentheses. And the output is represented by the entire quantity f parenthesis x. F by itself doesn't actually represent a number. This is not a number. This is just basically a label for the procedure that is being described here. For example, stop, drop, and roll is a label for the procedure that they recommend if you find yourself caught on fire. So in this case, f is just a labeling for a procedure, a function called f. But by itself, it's not a number. The x here is a number, and f parenthesis x is a number, but f by itself is basically text. It's basically just a label for this function, a name for this function. Let's get a bit more practice using function notation. They're describing to me the following function. They say if your input is t, here's what I want you to do. Take your input, square it. Take your input and multiply it by -3. Then add the results of the previous 2 steps, and then add 7. Now, writing that down in English is pretty annoying, so here it is in mathematical shorthand. So let's see if we can evaluate f of -1. Let's see if we can find the output if the input is the number in the parentheses -1. So following the instructions, I'm going to take that -1 and square that number. I'm going to take the number, -1, multiply it by -3. And then I'm going to combine those two results and add 7. So I get 1 plus 3 plus 7, and I get the number 11. That would be the output based on this given rule. Now, here's a slightly different question. They say solve f of t equals 7. In this case, this is a very different question because the input is not known. The number in the parenthesis is unknown. That's what we're trying to figure out. By setting the entire quantity, the entire f of t equal to 0, what they're saying is that the output must be 7. And they want to know that what inputs would result in an output of 7. So what I'm going to do is I'm going to take the entire output of the function f of t, and I'm going to set it to the desired value 7. And I'm going to algebraically determine the values of t that will make this equation true. So, for example, I can subtract 7 from both sides to get a 0 on one side of the equation. I can factor t times t minus 3 equals 0. And then I can use zero product property to say that t could be equal to 0 or t could be equal to 3. In either case, the product will be 0, which means that the function will output 7. These are the two inputs that will lead you to this desired output of 7. Now, one of the more unfortunate aspects of function notation, which I've never forgiven the larger math community for, is that function notation bears a disturbing resemblance to multiplication. You know, when we multiply two numbers together, one of the acceptable ways to multiply is to write something like a parentheses b. But for some reason, somebody's bright idea was to use exactly the same notation for multiplication. And because of that ambiguity, a lot of common errors are made by students who mix up multiplication and function notation. There are two important notes about function notation that can help you to avoid making these common errors. The first one is that although it is written using parentheses, function notation is not multiplication. Function notation does not behave like multiplication. Same representation in symbols, but completely different rule set. Another note that can help you sometimes is to say that if you ever encounter the label of the function, for example, f by itself, if f by itself ever appears in your expression or your equation, something's definitely wrong. You should never see a naked f. You should never see a naked f in your equation. It's violating public decency rules. Let's say that. F always has to be paired with an input. So f, if it's showing up all by itself in an equation, something's definitely gone wrong. A huge mistake has been made. F always has to be paired with an input if it's going to appear in an equation or in a mathematical expression. That's because f by itself is text, and plain text does not belong in a mathematical expression or an equation. The only thing that belongs in an expression or an equation are numbers or variables. So f of x is permitted, but f by itself is not permitted. No naked f's in your equation. So for some practice, let's have a look at a couple of common errors that I do see students make when working with function notation. And the first error is this. They have a function which is written in function notation as f of x equals x squared. The student is asked to find an expression which represents f of x plus h. Now, student number 1 says, aha, f of x plus h. Well, let me just distribute that f to the x and to the h separately So then I can find f of x plus f of h. So I'll square x, that's f of x, and I'll square h, that's f of h, and so the result is x squared plus h squared. The issue here comes in the very first step. They've tried to distribute, and distribution is possible when you're working with multiplication, but it is not possible when you're working with functions. Now let's look at a second attempt to find an expression representing f of x plus h. This student says, okay, so f of x is equal to x to the power 2, therefore f of x plus h must be equal to x plus h to the power 2. So they write down x plus h and then they write a little 2 upstairs. The issue here is that if we want to write down something that is mathematically equivalent to square the entire quantity x plus h, we need to make sure that the entire quantity x plus h is grouped together and that the square is being applied to that entire group. Now, without parenthesis, without grouping, the square only applies to the symbol which is directly underneath it. So in this case, this would only square the h. This is a common error that comes up quite often when students are asked to square negative numbers. For example, if they were asked to square evaluate f of minus 2, then a common error is to write down minus 2 to the power 2. But this is also wrong, because unless you group the 2 and the minus together, then any calculator is going to see this and think that you're only squaring the 2 and you're not squaring the minus as well. So if you wanted to square negative 2, you would have to group the 2 and the minus together before you squared it. Apply the square to that entire group. Let's look at another common error that arises when students are working with function notation. So a student is given the function f of x equals x squared again, and they want to find and simplify an expression which represents the fraction f of x divided by x cubed. So the student says, oh, aha, I have a fraction that has an x in the numerator and an x in the denominator. So let me just cancel those x's out, right? And I should get an answer which is equal to f divided by x squared. What do you think? Well, one sure sign that something has gone horribly wrong here is that this student has gotten a naked f in their fraction. F by itself, with no input, should never be in any mathematical equation or expression. The issue here is that, when we're simplifying a fraction, we are allowed to cancel common factors. So if I had 3 times x over x squared times x, then those x's would be common factors that I would be able to cancel out. The issue here, however, is that this expression in the numerator on the left side is not f times x. This is function notation, not multiplication. So because this is not actually multiplication, the x in the numerator is not actually a common factor that can be cancelled. So how would I actually answer this problem? I would say, okay, the f of x in the numerator, the output in the numerator, is the same thing as x squared. So f of x over x cubed could be rewritten as x squared over x cubed. I can replace the output f of x with x squared because they are equal. So now I have a common factor of x squared in the numerator and in the denominator. The numerator is equivalent to 1 times x squared, The denominator is the same thing as x times x squared. I have the common factors of x squared that I can cancel out, and that leaves me with the expression 1 over x. Now, to conclude this review video, I want to talk about one particularly sinister algebra mistake that has a way of haunting students throughout their entire careers. I will be teaching Calculus 4 or differential equations, and will still see the same mistake pop up from time to time. And I really have to wonder, how many points have been lost in total due to this one error? So the mistake is actually so famous that it has an official name. It's called the freshman's dream. And the situation where this mistake will arise is the following. Simplify the following expression. The first one that we're given is x plus 2 quantity squared. So here's the mistake. The student somewhere in the back of their mind remembers that if you have a product of two quantities raised to the power 2, then that can be expressed as simply 2 squared times x squared. That's because if I went back to the original definition of squaring something, 2x to the power 2 would be equal to 2x multiplied by itself, which after just a little bit of rearrangement is equivalent to having 2 2's and 2 x's, so 2 squared x squared. The student, with that in the back of their mind, thinks that they can do the same thing with a plus sign in between. So I will see this often simplified as x squared plus 2 squared, or x squared plus 4. The issue is that having a plus sign between the x and the 2 completely changes the game. In this case, if I went back to the original definition of square, and I wrote down x plus 2 multiplied by itself, then I find myself in a position where I need to distribute / FOIL. So x times x is x squared, and 2 times 2 is 2 squared. But I also get these extra 2 terms in the center, 2x and 2x. So this would be the true simplification of the expression given here. This error is so common that I really recommend that you memorize the following 2 formulas. A plus b quantity squared. How do you simplify that? You simplify that by taking a squared plus 2 times a times b plus b squared. A minus b quantity squared. How do you simplify that? That's equal to a squared minus 2 times a times b plus b squared. So, someone says simplify x minus 4 squared. I'm going to use formula number 2, which says I'm going to take x squared minus 2 times 4 times x plus 4 squared, which is 16. So that's x squared minus 8x plus 16. Someone says, what about 4 plus t squared? I'm going to use this formula here that tells me how to square a sum. So I'm going to square the first term, 4 squared is 16, and then I'm going to add 2 times 4 times t, and then I'm going to add t squared. So all in total, 16 plus 8t plus t squared. This would be the true simplification of this quantity. Now, related to this issue, you'll see a similar problem come up when students are working with square roots instead of squares. And again, the problem is the difference between multiplication and addition and subtraction. If I have a square root being applied to a product 4 times x squared, then I can split that up as the square root of 4 times the square root of x squared. So that would be equal to 2 times x. However, if you replace that multiplication with an addition, all of a sudden now you have a square root that can't be simplified at all.
Wait till you see the. No, 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 no.
This quantity is absolutely not equal to the square root of 4 plus the square root of x squared. Likewise, the square root down below, the square root of a squared plus b squared, is not equal to a plus b. As soon as you have an addition or a subtraction under the root, you have something that can't be simplified at all. Now in this case, we have the square root of 9 times 3. Multiplication. So this can be simplified. In this case, we can split up the root. Root 9 times root 3, which is 3 times root 3. But as soon as we leave multiplication and get back to addition subtraction, once again we have a root that can't be simplified at all. This is not equal to x minus y. This, you're locked. You can't simplify this even a little bit. Not at all. There is nothing simpler than this that is mathematically equal to this. So I've tried long and hard to come up with a way for you to memorize this situation with the square roots. And this is my best draft. This is my best draft so far. This rhyme here. Minus or plus, root makes a fuss. You make a fuss, you get mad, you get irritated, you throw a tantrum, you cross your arms. So if your square root has an addition or a subtraction under it, then your square root is going to throw a little tantrum, and you're not going to be able to work with it to simplify it in any meaningful way. This is my best attempt at a mnemonic for you. So I recommend to do whatever is necessary to remember this rule, that if your square root has addition or subtraction in the terms underneath it, then it cannot be simplified. It can only be simplified if you have multiplication or division. That concludes today's material. We reviewed circles and we reviewed function notation, and then we talked about the errors that I see students make all the time that cost them a huge amount of points throughout their math career.